This video is meant to introduce the periodic table. This is a pretty standard periodic table. There are about 118 known elements. They're arranged in columns and rows, and we're going to talk about why they have this arrangement. Now, some tables have some variability in the column numbering system or the placement of certain elements like hydrogen or lanthanum or actinium, but this is a pretty standard table. The periodic table was developed by Dmitry Mendeleev in 1869. Mendeleev was a Russian chemist. He looks kind of like Rasputin in this picture, so it's easy to remember that he's Russian. Named element 101 after Mendeleev. We call it Mendeleevium. And if we move on, so the idea behind Mendeleev's table is that elements in the same group or column, that, like for example here you see the first column, those elements share common properties. Remember, properties might be physical properties like you see on the left here, odor or color or density or hardness, state of matter at room temperature, is it a solid or a liquid or a gas, or they might be chemical properties. Is it reactive with air? Is it reactive with water? Things like that. So the elements shown here in group 1 share common properties with each other. Elements in group 2, the alkaline earth metals, share common properties with each other. These are the noble gases, and we'll talk about the specific properties that these groups have later. The elements shown here in green are the halogens. And so based on these common properties, that's why they are arranged the way they are, so that all of those common elements are in the same group or family, which is the. So the periodic table, the periodic refers to the fact that there are periodicities in the table, things that repeat over and over again. We'll talk more about that later. As I mentioned, it was developed by Dmitry Mendeleev in 1869. The elements are arranged based on the observed chemical and physical properties that he found in common in those families. We only discovered much later why those trends existed, so now we know why certain elemental families are more reactive than others, but at the time he did not know that. He also left spaces in the table for elements that had yet to be discovered. So for example, you see here his numbering scheme is based on the mass, not on the atomic number the way we number them now, because that was the observed property that he put in the table. He didn't really know what atomic number meant at the time. So he left a hole there for gallium, which had yet to be discovered. That's the element below aluminum that he has labeled 68. And he left a hole there for germanium, which had not been discovered yet either. He named those based on their placement on the table. He named gallium Eka aluminum because it's below aluminum, and he named germanium Eka silicon. So this is just another representation of the same thing. And he not only left holes for these elements, but he also predicted properties, and his predictions were actually relatively accurate once those elements were eventually discovered. So you can see his prediction in the third column here under Mendeleev's prediction and the observed property on the right-hand side. One interesting thing about gallium here, so gallium, it lists the melting point. Mendeleev predicted it would be, quote, low. So that would be the temperature where the solid converts into a liquid. Now you notice that the observed melting point of gallium is 29.8 degrees Celsius. Now I don't know how much you guys know about the Celsius scale, but room temperature, probably the temperature of this room that you're sitting in right now, unless it's very hot or very cold, is probably about 25 degrees Celsius. And so gallium would be a solid if you set it on the table. However, body temperature is 98.6 degrees Fahrenheit, which is 37 degrees Celsius. So if you put a piece of gallium in your hand, it would melt in your hand, right? So I think you guys probably know that mercury is the only liquid metal at room temperature, but gallium is close. Room temperature is just below its melting point. We're going to talk about these 5 bullet points one at a time. The first one we're going to talk about are the fact that the columns, the way that we arrange the elements with common properties, groups or families, and you can see those arranged here, right? Rows are called periods, and so you can see here row 1 is highlighted as red, and then period 2 is orange, and period 3 is yellow, and so on and so forth. The third point here is the difference between representative elements and transition metals. And so we can divide the table into those two types of elements. The representative elements are shown here highlighted in yellow, and so they are the first two columns and the last six columns of the table. They're called representative elements or main group elements, and they tend to follow the rules more than the other elements do, so they tend to be the ones that we use more in examples of things. They often have an A in their group identifier, so if you notice here, the columns are sometimes numbered consecutively 1 through 18, but more often, and the way I number columns is I simply number the representative elements only. So group 1A, 2A, all the way through 8A is the farthest right column. And you'll understand later why we number it that way. It's actually a hole in this table, right? There's a little hole there where lanthanum would be, and they've placed lanthanum with its series, with the rest of the element series. So element 57 is lanthanum, which is directly followed by the first in the lanthanide series, which is element 58, which is cerium, and that goes through element 71. And then you go back up to where we left off, and element 72 is hafnium. And then you continue down all the way to element 88 is radium, and element 89 is actinium. And then you can see that little dagger symbol is meant to show you that the next element after 89 is 90, which is down at the very bottom row, the actinide series. Element 90 is thorium, and that goes then through element 103, the end of the actinide series. And then you continue back up, 104 is rutherfordium, etc., all the way till the end. And so those inner transition metals are sort of called that because they're inside the other transition metals. Now let's talk about metals, nonmetals, and talk about some properties of metals versus nonmetals. So the metals comprise most of the periodic table. You can see what are shown in red here are metals, and with the exception of hydrogen, all the ones on the left-hand side of the table tend to be metals. There's sort of a diagonal line that separates metals from nonmetals. The upper right-hand picture is a picture of various metals, and so we're going to talk about different properties. Metals tend to be lustrous, which means shiny. They are malleable, which means we can hammer them into thin sheets. They are ductile, which means we can pull them into a wire. And they conduct heat and electricity. We're going to learn later why they have these properties. It's based on the structure of the atoms and the way the electrons move inside a sample. And then if we turn our attention now instead to nonmetals, there are some pictures of some nonmetals down here. The nonmetals are much fewer in number. They tend to occupy the upper right-hand portion of the periodic table, with the exception, of course, of hydrogen. So nonmetals are generally just, they are not any of the other properties. So they are not lustrous, they are not malleable, they are not ductile, and they are generally not conductive. Now malleable and ductile are listed here because whenever nonmetals are present as a solid substance, they tend to be kind of brittle or soft. So you can see the solids that are listed down at the bottom there tend to be they're not metallic like at all. They're powdery. But nonmetals are often gases or liquids. Okay, so it's very rare for a metal to be a liquid. Mercury is the only metal at room temperature that is a liquid. All of the other ones are solids at room temperature, but nonmetals are very often gases or liquids. Now semimetals, or metalloids, is another word for semimetal. So metalloids and semimetals, they tend to have properties that they share properties of both metals and nonmetals. So they have some of each. So they might be conductive, but they might also be soft or something like that, right? So they share different properties. And sometimes the metalloids themselves are useful to us because they have both properties, like silicon is a metalloid. So there's a picture here. The metals are shown in gray, the nonmetals are sort of this dark orange, and the metalloids are sort of this lighter orange. Now, the metalloids or semimetals, how those are categorized sometimes varies depending on the resource you use. For example, in this picture here, element 117 is not listed as a metalloid, but it is in some cases listed as a metalloid. So it just depends on the source, right? So there's some description. Now at the end, we're going to talk about some specifics. We'll start with the alkali metals. The alkali metals are in group 1A, and they do not include hydrogen. You can see hydrogen is removed from those. And so they start with lithium and go down sodium, potassium, etc. The alkali metals, this is a picture of, it looks like sodium, I think. They react very easily and they react violently with water. We'll do some of these reactions in class, but you've probably seen some of these reactions. Group 2 are called alkaline earth metals. They begin with beryllium, magnesium, calcium, etc. They tend to be relatively reactive. So alkaline earth metals are also considered, quote, active metals. When we say active metals, that means they are reactive, but they're not nearly as reactive as the alkali metals. And we'll talk about why. If we move all the way over to the right-hand side, we have the noble gases. Noble gases are also sometimes known as inert gases or rare gases, but noble gases is probably more common. So the noble gases start with helium as the smallest and continue down. Noble gases, like neon that you see in this pictured in this neon sign here, are extremely unreactive. And so and because they're so unreactive, we actually didn't even know they existed until the late 1800s. Most of the other, at least lower mass elements had already been discovered. Pierre Janssen and Norman Lockyer were the first to discover helium when they were looking at the chromosphere of the sun. And so they can look at the chromosphere and observe emission spectra, and they could see emission spectra of hydrogen, and they discovered that there was another element there. So they were the first to discover helium, and helium is named helium after Helios. I think it's Helios, which means the sun. So that was the first noble gas to be discovered. Lord Rayleigh and William Ramsay were the next to discover a noble gas at the end of the 1800s, not long after helium was discovered, and they discovered argon. Argon is part of our atmosphere, actually. So if you look at this representation of our atmosphere, it is mostly nitrogen with some oxygen, some argon, and then a little bit of carbon dioxide, and then, quote, other gases are listed in there. And that's going to depend on where you are, how wet the air is, right, the humidity, etc. So the reason that Lord Rayleigh and William Ramsay discovered argon was because they had isolated what they thought was pure nitrogen from the other components of the air. But it didn't have the same density as nitrogen that they had created in a chemical reaction. And so they deduced that it wasn't actually pure nitrogen, that there was still a substance in the air that was nitrogen mixed with something else that was changing its properties just a little bit from the pure nitrogen that they had created using a chemical reaction. And so they later isolated argon from the air. William Ramsay also went on to isolate other noble gases like krypton and neon. And there's another one, and I can't remember which one it is that he isolated. But anyway, so the noble gases were fairly late in the discovery, and that's just because they're so unreactive that they don't tend to form compounds and things like that. So they were late. So they're defined by their low reactivity. Now, just to the left of the noble gases are the halogens. The halogens are actually considered they are very reactive nonmetals, and you can see here the one on the left is chlorine gas, the one in the middle is bromine, and the one on the right is iodine. Chlorine is a gas at room temperature. Bromine is a liquid at room temperature, but you can see that it very easily volatilizes to form a gas. So there's a tiny bit of liquid in the bottom of that orange cylinder, and then it easily evaporates to form the bright sort of darkish orange gas, which is bromine. And then if you look at the iodine on the right is that purpley color, but there's some iodine crystals. Iodine is actually a solid at room temperature, but it very easily sublimes to form the gas. And so you can see the gases in here. Chlorine on the left is the only one that is a gas at room temperature. Bromine is a liquid and iodine is a solid. But clearly these are all colored gases. They're all very reactive. They're all also very toxic. Now, if we go through the symbols, a lot of the symbols make a lot of sense because they're just the first two letters of the name, like aluminum and argon and barium. Some of the elements don't seem to match because they are named for the Latin name, and you can see those kind of over on the right-hand side. Okay, copper is Cu and not Co because it is named because the Latin name is cuprum. And a lot of them are really weird, right? Like sodium is Na because its Latin name is natrium. Okay, so when they don't seem to match, it's because they are named, the symbol represents the Latin name. Now, I want you guys to know the names and the symbols of the following elements. Those are shown here. I based this on the most common elements that are out there. So, shown here on the table. And I think that you probably already know a lot of them anyway, but get busy knowing them as soon as you can. There's a little bit more here. These are just the relative abundance of various elements on Earth. You can see that oxygen is the most abundant element in the crust and in the human body, but you can see that here at 46.1%, and some various others. The ones that don't show up here have very minimal abundance. And then here, relative abundance in the human body. Oxygen is, of course, still very high. Carbon is also very high. There's some interesting URLs here for fun element songs if you're interested. We're going to do this practice problem real quick, and then we're going to move on. Identified by capital letters each of the following elements. So we're going to start with part A, the halogens. Okay, so the capital letters that are on the table, the halogens, remember, are the group that are almost all the way to the right. They're right next to the noble gases. It's group 7A, so that's here. So element F is the answer to part A. B, the element that is definitely a gas at room temperature. Well, a lot of these are metals, and I know that most metals are solids at room temperature. And I know the far right-hand column are known as the noble gases, and so therefore I know that element G is a noble gas, so it must be a gas at room temperature. Part C, the metalloid. There's only one, so you don't have to memorize exactly what the metalloids are. But I generally want you to know that they're sort of along this diagonal line over here. And so the only thing that might touch that diagonal line is E. And so knowing that there's only one means that E has to be the answer. Okay, so there's a diagonal somewhere in that area, so E has to be the answer. D, the nonmetals. Okay, well, if E is a metalloid, that means F and G must both be nonmetals. The metals are everything else. A, B, C, D, and H are all metals. F, the representative elements. This is just to remind you that these are the intertransition metals that go here. The representative elements are anything that is not a transition metal. Okay, so groups 1 and 2, the first two columns and the last 6 columns are all representative elements. So A, B, and C are representative elements, and E, F, and G are representative elements. And then the transition metals are everything else. D and H are both transition metals. And then the intertransition metals is a more specific question, and the answer to H is H. Actually, there's only one intertransition metal listed here, and that's H. That was just a coincidence. Those happen to be the same letter. Now, part I is asking about alkali metals. That's the first column, so A and C are the two alkali metals listed here. The alkaline earth metal, the only one here is B, because that's group 2. The last question here, the element that is probably most similar to element A in chemical properties is going to be element C. It's going to be whatever is in the same column or family or group, right? So it's going to be C. Now we're going to move on. There's one other question here about classifying matter. Consider each drawing and classify each one as a mixture or a pure substance. If it is pure, is it an element or a compound? If it's a mixture, What is it a mixture of? Is it an element and a compound? Is it two elements? Is it two compounds, etc.? So if we categorize these, it looks like A is pure because it only has one substance. That substance is a compound, right? So A is a pure compound. B is a mixture, and C is also a mixture because there's two different substances present. B is a mixture of these things, which look like one big sphere and two small spheres connected, like maybe water. And this other one is two, so it's two different compounds. B is a mixture of two different compounds. And I know it's a compound because each of these has at least two elements present. So A is a pure compound, B is a mixture of two compounds, and C is a mixture of one element. These two, the fact that they're both white implies they are the same element. The fact that one of these is black and the other one is white implies that they are two different elements, which means they are a compound. So C is a mixture of an element and a compound, one element and one compound.